I was thinking we could kick it, and you be my Neruvian empress. I promise that only dreams we will witness, but you seeing something different. I know that it's your mind, not your intuition.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now let's talk about electron affinity. And so as the name suggests, electron affinity is the ability of an atom to accept an electron. But unlike electronegativity, which I'll talk about in a second, electron affinity is a quantitative measurement of the energy change that occurs when an electron is added to a neutral gas atom. So I can actually write this out as whatever element X in its gas form gaining an electron then becomes the negative form, and the electron affinity, let's say energy EA, the energy of electron affinity, is equal to the energy of the original element minus the energy of the negative form. Okay, but now let's talk about the trend. So electron affinity generally decreases down a group of elements, so it actually follows a similar trend to electronegativity. And this is because of the atomic radius trend that we discussed before. This means that an added electron is further away from the atom's nucleus compared with its position in the smaller atom. So we talked about that before, and if you need to remind yourself, you can go back to when we talked about atomic size. So with a larger distance between the negatively charged electron and the positively charged nucleus, which is what we keep talking about, the electrons are negative, compared to the force of the attraction, it's relatively weaker, and therefore electron affinity decreases. Now moving from left to the right across a period, atoms become smaller as the forces of attraction become stronger. Again, we mentioned this before. This causes the electron to move closer to the nucleus, thus increasing the electron affinity from left to right. And thus, the trend here is like so, for the most part. But electron affinity is not as periodic as the other trends that we've talked about, but generally, there is a high electron affinity for elements in the top right of the periodic table, so like group 17. So another thing that I wanted to mention is that adding an electron to a filled valence shell, a noble gas, is very unfavorable, and energy is required to do that. And so, as I mentioned before, when we talked about ionization energy, noble gases are the most stable, and it doesn't want to lose or gain electrons. So now, as we're going through these periodic trends, you can see how they link together, how atomic radius, how ionization energy, electron affinity, all of those are connected based on the different elements. So finally, we talk about electronegativity. So this can be understood as the chemical property describing an atom's ability to attract and bind with electrons. So since this is a qualitative property, there's no standardized method for calculating the actual values. And so we talked about electron affinity as a better way to quantify. And so since electronegativity measures an atom's tendency to attract and form bonds with electrons, this property exists due to the electronic configuration of atoms that we also went over. So most atoms follow the octet rule, having the valence or outer shell comprised of 8 electrons. And because elements on the left side, right here on the periodic table, have less than a half full valence shell, the energy required to gain electrons is significantly higher compared with the energy required to lose electrons. So as a result, the elements on the left side of the periodic table generally lose electrons. So let me write here, lose electrons when forming bonds. On the other hand, elements on the right side of the periodic table are more energy efficient in gaining electrons to create a complete valence shell of 8 electrons. So let's say gain electrons. So just to show you an example, if you have lithium, I've been using this example a lot, but since it just has 1 electron in its valence shell, it's a lot easier for this to lose an electron rather than gain 7 electrons in order to get an octet. On the other hand, if we have fluorine that has 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now instead of losing the 7 valence electrons, it's a lot easier to gain 1 electron right here. So the nature of electronegativity can be described as the inclination an atom has to gain electrons, and the more likely that atom will pull electrons towards itself. So as you can see from these arrows, electronegativity increases up a group, and it also increases across the period. And so there's important exceptions to the rules that I just talked about, which include the noble gases, lanthanides, and actinides. So since noble gases possess a complete valence shell over there, they don't usually attract electrons. They're happy, they're stable, they want to stay that way. The lanthanides and actinides possess more complicated chemistry that doesn't really follow any of these trends, the guys that are down here, so you can ignore them for now. And as for transition metals that are all in here in the blue, although they have electronegativity values, there is little variance among them across the period and up and down a group. And this is because their metallic properties affect their ability to attract electrons as easily as the other elements. So here I conclude with talking about all 4 periodic trends that are extremely important for you to understand conceptually so you can do problems in this chapter.
Girl, I'm thinking that you're beautiful, and I can tell by your eyes that you feel me too. So why do you feel the way that you do? Why do you